too early to talk 6G? Not for wireless communications researchers. Research for a new generation of mobile wireless communications starts more than 10 years ahead of initial deployment. Launching 6G in 2030 means research has already begun. 6G will allow new, exciting use cases above and beyond 5G by combining sensing, imaging, precise timing, and intelligence at the edge with the mobility of wireless. It will further integrate communication and compute technologies into society, including using and expanding AI applications. Early 6G performance targets represent a 10 to 100 times increase over 5G, up to 1 terabit per second peak data rates, connection density of over 1 million devices per square kilometer, and centimeter-level precision positioning. Frequencies above 100 GHz will enable ultra-high data rate short-range networks. Precise timing requirements will bring time-engineered networks and applications and will require changing how networks operate. Delivering 6G demands significant advances in computing and networking architectures, chipset designs, radios, antennas, and materials. Exponential growth in data traffic will bring spatial spectral efficiency and connectivity challenges. Extreme modulation bandwidths and shorter wavelengths will reduce beam width and increase antenna and device integration. Radio resource optimization and intelligent networking will also require innovation in RF, baseband, and system design. Significant technical challenges are on the horizon for wireless design and test engineers. While continuing to enable 5G development and deployment, Keysight is also active in 6G programs around the globe, working on solutions for the 2030 wireless era. Our current solutions provide advanced capabilities that test far beyond 5G. With Keysight, you can build 5G today while preparing for 6G tomorrow. Explore your options today.
Good morning, good afternoon, everyone. Welcome to Keysight Technologies virtual event series. We are pleased to have you here for today's virtual event on understanding sub-terahertz channel sounding and FPGA customization of a 6G testbed receiver. My name is Girish Baliga from Keysight Marketing, and I'm the moderator and presenter at today's webinar. Today, we'll be spending the next 45 minutes or so deep diving into understanding sub-terahertz channel sounding and FPGA customization of a 6G testbed receiver. Before we get started, couple of housekeeping inputs. During the presentation, you can dial in your questions in the Q&A box on the streaming console. We'll be more than happy to answer your questions and get back. Also, please share your recommendations on the survey form, which will appear as a pop-up during the course of the webinar. There is resource collateral on understanding sub-terahertz channel sounding and FPGA customization of a 6G testbed receiver on the webinar console. You can download these two from the resource list. In addition, please share your comments about the program as well, enabling us to serve you better. And please use audio headset or earphones to listen to the virtual event audio for good audio effect. Like I mentioned earlier, I will be presenting today's paper on understanding sub-terahertz channel sounding and FPGA customization of a 6G testbed receiver. I manage the marketing for 5G wireless, wireline, aerospace defense, and software at Keysight Technologies. Without much ado, let us begin the session. "6G or sixth generation wireless is the successor to 5G cellular technology. 6G networks will be able to use higher frequencies than 5G and provide substantially higher capacity and much lower latency. The 6G technology market is expected to facilitate large improvements in the areas of imaging, telepresence technology, location awareness, and so on and so forth. Working in conjunction with the artificial intelligence, machine learning, cloud computing, as well as the edge, the 6G computational infrastructure will be able to identify the best place for computing to occur. This also includes decisions about data storage, processing, and sharing. In the innovation age, technology advancements are always in development. The next generation of cellular technology will make huge improvements in bandwidth utilization, data delivery, and application enablement. It is expected that 6G will offer download speeds approaching 1 terabit per second, 1 microsecond latency, and unlimited bandwidth. 6G will enable ingenious ways for people to interact with their surroundings, including instantaneous communication, connected robotics, and autonomous systems, in addition to what I mentioned before. With the deployment of 5G well underway, we are seeing how vendors and service providers are able to help consumers, industry, and the government unleash a multitude of use cases with far reaching benefits. However, 6G will go much further. 6G will see the development of technologies which will create new worlds, blending the physical and virtual, providing unprecedented levels of performance, reliability, and security. Society will be fully connected for the first time. Physical and cognitive augmentation will make humans far more efficient and productive than we are today, making use of the ubiquitous nature of 6G, while new industries and business models will be enabled. Part of the 6G vision is also to support and enable sustainable development goals, promoting global health, education, quality of life, justice, and inclusion for all. A wide range of technologies such as AI or artificial intelligence, advanced sensors, optics, cloud computing, high-speed digital, satellite and robotics will undergo rapid advancement in the next decade, combining and augmenting to enable new use case models made possible with 6G. Here are some examples which I would like to highlight here. In the areas of communication, 6G will bring multi-sensory technologies to create new ways to people to interact with each other and with their surroundings using not just sight and sound but touch, smell, and taste as well. 6G will eliminate physical and temporal distance between human beings through holographic imaging and seamlessly connecting human to human and human to machine worlds. Networks will be powered by artificial intelligence, allowing fully automated infrastructure automation and as well as optimization and service provisioning. There will be widespread use of digital twins, exact real-time replicas of physical processes, and virtual models using past and present data with machine learning to dynamically monitor, improve, optimize, and enhance many such different processes. Technologies employing extremely precise timing and orchestration of data will transform manufacturing and industrial processes as well as the networks that serve them. The environment in which all inclusive communication will be available will extend to land, sea, air, and space. Finally, 6G will significantly improve society's ability to respond to and manage emergency situations whenever they arise. Let us consider some of the areas of technology which will need to be developed over the next few years. 6G applications and use cases will drive the need for much higher data rates than for 5G, pushing the industry to exploit the spectrum at much higher frequencies above 100 gigahertz, as well as making full use of the available spectrum below 100 gigahertz. Spectral efficiency, energy efficiency, and waveform design will all play a crucial role in realizing these high data rates. A characteristic of the vision of ubiquitous wireless connectivity will be the coexistence and seamless integration of heterogeneous radio access technologies far beyond what is experienced today. Flexibility and adaptability will be enabled by advanced network management powered by artificial intelligence, and new use cases will be realized through the concept of time engineering. Low latency, while critical in many applications, will also be augmented by time predictability, where the absolute time of arrival of data also carries information, and by time synchronization to a very high degree of precision. With such dramatic changes in the interaction of humans, machines, and the connected world, trust and security must be designed in from the beginning using powerful and agile detection, mitigation, and preventative techniques. The rapid transformation to an always on world of connected networks, defined and managed by virtual machines, will present a significantly larger threat surface than today. The consequences of malicious hacks and data breaches are already extremely severe. 6G must therefore achieve much higher levels of sophistication in detecting threats, neutralizing them, and building in advanced security hardening. Key performance indicators for 6G are significantly beyond what was envisioned for 5G. The radar diagram illustrated here depicts a selection of the KPIs which major stakeholders are signaling in their respective white papers and other public communications. In most cases, we see at least an order of magnitude difference from 5G to 6G in terms of connection density, throughput, latency, reliability, and energy efficiency. The industry has yet to reach a consensus as research is still in its infancy, and technology boundaries as well as end user requirements are still being developed. The two bold lines in the diagram, what we might call conservative or probably cautious estimates, and ambitious or bold estimates. As you can see, the scales on this diagram are logarithmic. So now let's pause and take a look at where the world is in its current 5G journey. Over the past 2 3 years, the industry has witnessed several key success markers in an industry transitioning towards full 5G capability. 5G deployments have more than doubled, with more than 200 mobile operators in more than 100 countries having launched commercial 5G services. According to the Global Suppliers Mobile Association, there are around 500 mobile operators around the world investing in 5G. Although 5G accounts for less than 1% of the global connections, it is expected to reach around 20% of global connections by the year 2025, which is an increase of nearly 2,000 in next 3 to 4 years. Over the course of the next decade, cross industry collaborations and a complex web of technologies will reshape businesses, industries, and our lives. This timeline shows how we expect the evolution of the 5G standard driven by 3GPP to roll out alongside the development of 6G technologies and standards. Toward the left of the diagram, we see the timing of Release 16's performance requirements, followed by Release 17 in mid 2022. We should also expect to see agreement on the scope of Release 18 at about the same time. Release 16 and 17 and beyond, as known as the 5G evaluation, enhancements and extensions of the original Release 15 5G standard. In parallel with the evolution of 5G, 6G research is already underway in many areas. building upon 5G while developing new and unique capabilities. We will see an increasing number of variety of technology demonstrations and trials augmented by the 6G test beds, such as the test networks of all types, taking us through to around 2030. 6G standards works is expected to begin in all earnest around 2024, becoming 3GPP release 20 probably, which is likely to be deployed before the end of this decade. As happened with 5G, there will be a race to declare the first commercial 6G service toward the end of the decade. In the years that follow, we will see successive waves of 6G technologies being brought to the market, fulfilling the 6G vision throughout the 2030s. There are many research challenges to overcome before reaching commercially viable 6G deployments. 6G products, services, and applications, while in some cases revolutionary, but in some cases will be leveraged from 5G technology and would need to coexist with the current 5G technology. Others may be completely new and require the development of novel techniques and processes. Given in this slide is a short list of current research topics which will provide the foundation for 6G. This would include in all areas, including wireline, wireless, non-terrestrial networks or NSN, the NTN, data analytics and security, as well as the fundamental areas of physics. Keysight is building on our expertise and influence as the market leader to develop interdependent technologies and solutions to the industry. We are able to bring interdependent technologies and solutions to customers, which allows the realization of the necessary building blocks, the linkages, and the interfaces of a multifaceted 6G ecosystem. Our emphasis is on providing excellence in customers' end-to-end experience, starting with comprehensive electronic design software coupled with integrated software-centric measurement platforms with the outstanding hardware instrumentation, as well as providing the right solutions with by making innovative leaps in technology, products, solutions, and applications. And 6G is no different. At Keysight, we have enabled a great majority of 5G customers to successfully commercialize by driving the latest standards and providing the integrated workflow solutions at the pace of the market makers. Cloud-based software-centric solutions are enabling the industry to implement virtualized radio access networks, aka the Open RAN, facilitating disaggregated network architectures and network slicing. Our integrated portfolio from the edge of the RAN to the core of the network has allowed customers to verify performance, interoperability, and conformance to ORAN standards, thereby supporting mobile operators' transitions towards open virtualized RAN deployments. In the UE conformance test, we have the industry leading over the air or OTA solutions for testing 5G FR2 devices, which have laid the foundation for technology which is critical to 6G. On top of it, we are building on that success to verify and test CPEs, small cells, and radio units for deployment in FR2 networks. And we also made significant advancements in 5G NR, PCI Express, USB, Open RAN, Wi-Fi 6, and others. And by part of setting the standard, we ensure deep expertise that resides throughout the organization. We have had the first to market high-speed digital test solutions for Terahertz solutions, which have enabled hyperscale and edge data centers to support the capacity, latency, and speed that is required for technologies beyond 5G. Our unmatched expertise and agility to create necessary linkages within 6G and adjacent technologies, which are critical in delivering the broadest set of solutions for the complete end-to-end enablement of future wireless ecosystems. And that would also involve adjacent technologies, which include timing, security, sensors, optics, energy, power, satellite, and so on. Our solutions are built on common software platforms such as Pathwave that address the entire workflow from design to verification to optimization through to manufacturing test. To overcome some of the early 6G research challenges, we at Keysight have developed a sub-terahertz test bed that is already in use by wireless companies to develop high frequency, high bandwidth transceivers. This system provides high quality measurements with low residual error vector magnitude or EVM using very wide modulated signals in the gigahertz range in carrier frequency with full support with our vector signal analysis or VSA software. The Pathwave system design software tool, which is enabling the 6G PHY design, waveform creation, and advanced beamforming. Additionally, the 6G testbed can be used for high frequency channel sounding, which is considered essential in developing an air interface technologies above 100 gigahertz. We are providing the industry leading high speed real time oscilloscopes with ultra wide bandwidth and waveform generators and digitizers, network and spectrum analyzers and signal sources. So we will understand more about the sub-terahertz channel sounding and FPGA customization of a 6G communication system in the ensuing slides. Switching gears, now let us understand channel sounding using a sub-terahertz test bed. Getting back to basics, channel sounding is the process of measuring the response of a channel to an impulse. If the channel is linear and time invariant, you can predict the response to any signal input into a channel. The system computes the response to each impulse in the input signal and adds the output responses together to get the total output response to the signal. This process is known as convolution. The channel sounding procedure includes three key steps. The first step is to send a known signal into the channel, and the second step is to capture the signal after the channel. And the final step is to compute the channel response by comparing the transmitted signal with the received signal. As you can see from the block diagram here, it shows a free space environment that contains several reflective objects. When the antenna transmits a channel sounding signal into this environment, the acquisition hardware captures the signal power that reaches the receive antenna. One can analyze the signal power using channel sounding software. Our 6G specialist will talk about this and more with respect to 6G channel sounding in a detailed demo in the next slide.
Hi, my name's Caleb Doherty, and I'm an R&D engineer on the Keysight Pathwave 89600 VSA team. I'd like to introduce you to our channel sounding solution, why you might want to use it, how it works, and what results you can measure. Here we have a channel sounding measurement at 144 GHz. On the right, you can see the time and frequency domain plots of the channel response. The frequency response is the blue trace in the upper right, and the time domain response is in the red trace below it. The red trace shows the reflections of the impulse sent into the channel. The peak is placed in the middle of the trace at time equals 0. In this particular measurement, there are two main peaks and several other smaller peaks. Then there is a lower level of power underneath all distinguishable peaks. This power tapers off into the noise floor as you get out further into time. Later, I'll explain this scenario in more detail, but first let's get a high-level view. The basics. Channel sounding is the process of measuring the response of a channel to an impulse. When you know this information, assuming your channel is linear and time invariant, you can exactly predict what the response will be to any signal you put into the channel at any time in the future. This is because the signal can be expressed as a linear combination of impulses. You simply compute the channel's response to each impulse in your signal, and then add the responses together to get the total response to your signal, a process also known as convolution. Note that a channel can be anything in between the output of the sounding signal and the input to the analysis hardware. In a nutshell, the channel sounding procedure is 1. Send a known signal into the channel, 2. Capture the signal after the channel, and 3. Compute the channel response by comparing the sent signal with the received signal. Let's take a look at one particular channel in a top-down view. This channel is a free space environment that contains several reflective objects. If we send a signal into this environment using an antenna, in this case using Keysight's custom modulation signal studio software connected to a signal generator, the signal will disperse and reflect off the objects in the channel. The power that makes it to the receive antenna can then be captured by the acquisition hardware and analyzed by the channel sounding software in the Pathwave 89600 VSA software. Okay, let's stop a minute and ask why. Why do people need to measure channels? One common use case is a network measurement. Although a network analyzer might be more appropriate here, you can measure the S21's frequency response of a two-port device with channel sounding. Another use case is end-to-end calibration. You have a signal generator and are going to test the EVM of a device with a particular modulation, but you want to remove the effects of the test fixture from the measurement results. Lastly, an area of research that is active during the creation of this video is 6G research into higher frequency bands. Sub-terahertz frequency bands, those that are 100 to 300 gigahertz, are of interest for 6G research because wide modulation bandwidth could potentially be used to achieve data throughput exceeding 100 gigabits per second. However, these frequency bands are relatively new and uncharacterized, so channel sounding may be needed as part of early 6G research. For example, what does the channel look like when you transmit inside a building? Or what is the difference between wood and concrete buildings? These are the kind of questions that can be answered by channel sounding. Now, some particular features of the Signal Studio and 89600 VSA channel sounding solution are a support for a variety of transmit and receive hardware, multiple receive channels. So for instance, you can simultaneously measure the receive signal from different directions, low SNR support through signal averaging, and lastly, no need for any cables between transmitter and receive hardware, making it easy to position them at various locations in the channel, potentially very far apart. Now let's get back to the example I showed you at the beginning of the video. Here's our channel. We have two reflectors in an RF chamber. The reflectors are made of boards covered with aluminum foil and mounted on tripods. Then we have our transmitter and receiver on a table at the back of the chamber. Here's the top-down view. The black rectangle represents the table, and the orange boxes represent the instruments on the table. There are two signal converters, each with a horn antenna, and I'll show you close up in a minute. The two reflectors are placed at roughly 1 meter and 2 meters away from the transmit and receive antennas. When the sounding signal is transmitted, the receive antenna will see two main reflections of the transmitted signal, separated in time. Okay, here's the close-up of Keysight's new sub-terahertz testbed for 6G research. This testbed has also been demonstrated in measuring EVM at D-band, which is 110 to 170 GHz, and G-band, which is 140 to 220 GHz, which you can find more info about at www.keysight.com/find/6G. But here we are using the same hardware setup to perform channel sounding. On the left, we have the 89600 VSA software and Signal Studio software running in a controller PC card in the AXIE chassis. The Signal Studio software sends the signal to the M8195 AWG, which is also in the AXIE chassis, and the 89600 VSA software captures the data from the UXR oscilloscope on the right side of the table. The 89600 VSA software could easily be run on the oscilloscope, or even on another computer on the network. The signal from the M8195A AWG is transmitted at a symbol rate of 4 gigasymbols per second and a center of 6 gigahertz. This signal is upconverted by the VDI converter to a center of 144 gigahertz and transmitted using a horn antenna with a nominal beam width of 9 or 10 degrees. The PSG behind the converters provides a local oscillator signal for both converters through a splitter. The LO could have been provided by separate instruments, but since the transmitter and receiver were co-located, we connected it this way for convenience. Then the down converter shifts the signal back down to 6 GHz, and the signal is captured by the oscilloscope. Let's walk through the procedure. So here I have the N7608C custom modulation version of Signal Studio. It can create many types of signals, but here I'm going to select channel sounding from the shortcut by modulation menu. Normally the first step would be to connect to your signal generator. Since I've already captured a recording of the channel sounding signal in the RF chamber, I've just selected a simulated M8195 for now. Okay, now that we've selected the channel sounding signal, we can configure the parameters. I chose a sequence length of 512 symbols and a symbol rate of 4 gigasymbols per second. I left the filter and multipath parameters at the defaults. Once you finish configuring these parameters, you can click the download button, and that will generate the sounding waveform and send it to the AWG for playback. Now let's switch to the 89600 VSA software. To configure the VSA for channel sounding, the first thing would be to connect to your measurement hardware. But in this case, I've already loaded the recording of the sounding signal into the VSA. This particular waveform was captured at a center frequency of 6 GHz after down conversion from 144 GHz. I configured the user correction properties of the VSA so that the user interface correctly reflects the 144 GHz signal center before down conversion. The next step would be to set your measurement span, which in this case is 4 GHz. Typically, you would just set the span the same as your sounding symbol rate. Now we need to configure the channel sounding measurement. First, I'll go ahead and select the channel sounding measurement extension. And the parameters for configuring the measurement are located on the channel sounding properties dialog. The only two parameters I need to configure here are the sequence length and symbol rate. Since we are using matched RRC filtering, the filter parameters need to match Signal Studio. Otherwise, you can configure the filter parameters according to your needs. For example, to reduce the effect of side lobes, you might select a Gaussian filter. Okay, now that that's set up, let's run the measurement. On the left side, we can see the basic spectrum and some signal metrics. The spectrum is useful to verify that your signal is present, and the metrics can give you a sense of whether there are any impairments that might affect the measurement of the channel. On the right side, we have the frequency and time domain versions of the channel response. The trace that is of most interest for this example is the impulse response. This trace shows the various reflections in the channel. This includes their location and time, their amplitude, and if you were to select a different trace format, their phase relative to the measurement carrier. If the channel was a purely flat channel, you would see only one path. Depending on the physical arrangement of transmitter and receiver, you can interpret the paths that you see in the impulse response. If the transmitter and receiver were on either end of the room, you could interpret the highest path, which incidentally is always placed in the center of the impulse response, as the direct line of sight path, and the other paths as reflections off the walls of the room. In our example, though, both the transmitter and receiver are located in the same plane and are pointed at objects in the room. The highest path in an impulse response may not be the first reflector, depending on how absorptive the reflector is relative to the others. But in this case, both reflectors are made of the same material, so the amplitude difference that you can see between the two main peaks can probably be attributed to free space loss or to slight beam misalignment. Anyways, in this impulse response, we can interpret the first peak as the closer reflector and the second peak as the second reflector. Electromagnetic waves travel approximately 300 millimeters per second in air. Inverting this value gives us 3.33 nanoseconds per meter traveled. Since the path difference between the two reflectors is 2 meters, we should see approximately 6.7 nanoseconds between the paths. Let's make a rough measurement by using delta markers. I'm going to go ahead and close the frequency response for now. First, we place a marker on the peak. Then select 0 delta, so we get a second fixed marker at the same location. Then I can move the first marker to the second peak. We can see that the time difference is about 7 nanoseconds, which is close to the 6.7 nanosecond value that we just calculated. The other smaller peaks are probably reflections off the instruments and walls of the room. As the signal continues bouncing around the room, the power decreases and you can see a gradual decay of the power over time. Okay, another thing. If we look at the main peak, we can see that it is about 45 dB above the noise floor. Can we do better? Some of the noise can be assumed to be Gaussian and as such uncorrelated across time. This means we can average multiple channel response measurements and the uncorrelated part of the noise, if we do vector averaging, will average towards 0. There are two ways to do this in the channel sounding measurement. One is to increase the number of repeats parameter. This will acquire a longer time record and average the repetitions of the impulse response together. This method of averaging is useful to dig the signal out of the noise when the measurement is having trouble synchronizing. However, the measurement will update slower and be more sensitive to symbol clock error. The alternative is to enable VSA measurement averaging, which you can do by selecting RMS video averaging in the Mesh Setup Average dialog. I'll select the exponential version so the average keeps being updated after the count has been reached. Note that this parameter serves a dual purpose. It enables measurement averaging and also specifies the default average type. The measurement can choose a different averaging method if RMS is not appropriate. For example, the yellow spectrum trace on the left is RMS averaged, but the frequency and impulse responses are vector averaged. In both cases, averaging is performed point by point, but in the case of vector averaging, the complex values are averaged instead of the squared magnitude. Note that the time alignment the measurement performs before averaging is done without the need of a hardware trigger. There's enough time data in this recording for about 500 averages. Perhaps you didn't notice, but the noise floor decreases quickly at first and then slows down. I'll go ahead and restart the average so that you can see that. Eventually you'll reach a limit. This is due in part to the residual frequency and symbol clock errors in the measurement, which prevent the sounding signal from modeling an ideal impulse and instead being an impulse with some very low amplitude side lobes. However, we can see that now the noise floor is about 70 dB below the main peak, an improvement of 25 dB. One last thing to mention is that the channel sounding solution supports multiple receive channels. This allows you to measure the relative differences between channel responses. This could be antennas with different polarizations or antennas pointed in different directions, or some other scenario. So, thanks for watching this video, and before you go, here are some links to find more information about Keysight's products and solutions. Also, you may be interested in the flex frame measurement provided by the 89600 VSA. Instead of being a standards-based modulation analysis tool, it allows you to define and analyze your own custom frame. This could be helpful in your 6G research as you prototype different ideas for the next standard.
Thank you, Caleb. Now we will shift gears and understand more on the second aspect, which is the FPGA customization of the test bed receiver. As you can see from this particular slide, you see a block diagram which talks about the FPGA customization of a sub-terahertz test bed receiver. As you see, the red box in the slide represents the FPGA customization, and which is implemented with the PathWave FPGA. As you see here, an FPGA yellow block down converts the IF from 6 GHz to a complex baseband. A magnitude trigger will provide the coarse time alignment of the receive waveform with the 65 gigabits per second AWG, which acts as a reference in the equalization process. A sample shift block refines the time alignments and further aligns the receive waveform with the reference waveform after magnitude triggering. The green box represents the PathWave test automation control and software visualizer that displays the IQ constellation, BER versus time, and equalizer frequency response after performing the fast Fourier transform algorithm to convert the FIR time domain coefficients to the frequency domain. To talk about this and more, we have Greg Ju from the 6G specialist who is going to talk about this in the form of a demo. Over to you, Greg.
Hello, my name is Greg Ju with Keysight Technologies. I'm a system engineer working on Keysight's 6G testbed. Sub-terahertz frequencies are of interest for 6G. In fact, it's a very active area of research. And the reason is sub-terahertz frequencies offer large, contiguous swaths of spectrum that could potentially be used to help achieve high data throughputs of 100 gigabit per second to a terabit per second. However, these sub-terahertz frequency bands are largely unexplored. So 6G researchers are going to want to do things like channel sounding to understand propagation characteristics, and eventually receivers will have sophisticated baseband algorithms to be able to address channel impairments. So today we'd like to show Keysight's sub-terahertz testbed for 6G research. Now we've shown this testbed before for wideband EVM measurements, and it can also be used for channel sounding. But today we'd like to show how the Keysight sub-terahertz testbed receiver can be customized with the user HDL code. Specifically, we're going to show a customization example, which is an FPGA real-time adaptive equalizer implementation. So the test setup consists of an M8195A AWG. This is used to produce a wideband IF, which is run into a Virginia Diodes Incorporated or VDI up converter. The signal's upconverted to 144 gigahertz. It's then amplified, filtered, and transmitted over the air with this horn antenna. The signal is received with this horn antenna, down converted back down to an IF, and the IF is run into the M8131A digitizer. Now you'll notice that there were optical links connecting the digitizer to this M8132A DSP module, and this is where the FPGA customization is going to occur. So with this, I'd like to introduce my colleague Eric, and he's going to take us through the FPGA implementation and do a live demo.
Thanks, Greg. Hi, my name is Eric Wilson, and I am an FPGA engineer with Keysight Technologies, and I will be walking you through the system-level block diagram of the 6G channel equalizer solution. So once the 144 gigahertz transmit signal is received, it is down converted to an IF of 6 gigahertz and digitized with the M8131A digitizer. The digitized data is sent over an optical connection to the M8132A, a DSP processing module. This module has 2 FPGAs in it, and our channel equalizer is implemented in both FPGAs. The digitized data is first down converted to baseband with an LO block, and then we trigger on the beginning of the waveform. The waveform data is oversampled by a factor of 4, and the channel equalizer runs at the symbol rate. So we need to use a root raised cosine decimating filter to decimate down to the symbol rate. Once we are down at the symbol rate, the data is sent across an inter-FPGA link to the second FPGA with the channel equalizer. The channel equalizer will equalize the IQ symbols, and we send the equalized IQ symbols up to the host PC. We also send the equalized IQ symbols through a bit error rate block that will calculate the bit error rate results, and we send that up to the host PC along with the channel equalizer coefficients. On the PC side, we use Keysight test automation software to plot and visualize the results, and we were able to plot the IQ constellation, bit error rate versus time, and channel equalizer frequency response. And now I'll do a live demo of the 6G system running. On the screen on the top trace, we have the equalizer frequency response. On the lower left trace, we have the bit error rate versus time. On the lower right trace, we have the equalized IQ symbols showing a transmit waveform with an 8 gigahertz symbol rate and an occupied bandwidth of 10 gigahertz. I'll now demonstrate blocking the RF channel with an object, and we will see that the bit error rate goes up to 50% and the IQ constellation plot becomes distorted. When I remove the object and the channel returns to normal, you'll see that the bit error rate goes back down and the IQ constellation plot returns to normal. I'll demonstrate this again by taking the object and placing it in the RF path, and we can see the bit error rate increases and our IQ symbol plot is distorted. And once again, when I remove the object, the channel returns to normal. Thank you for your time today. For more information, please contact Keysight Technologies.
In summary, 6G research requires channel sounding at sub-terahertz frequencies to determine the channel propagation characteristics. Key metrics including EVM bit error ratio and data throughput to achieve individual rates of around 100 Gbps or more is the order of the day. Wide modulation bandwidths of up to 10 gigahertz occupied bandwidth introduce significant linear amplitude and phase impairments for both radio hardware and the channel. One can mitigate this impairments with the receiver baseband algorithms to optimize data throughput and minimize BER. In addition to measuring waveform quality, Keysight's sub-terahertz testbed can also perform channel sounding using channel sounding signal generation and analysis software. One can also add a DSP module to customize the testbed receiver with custom proprietary algorithms. And this approach also enables other FPGA implementations for 6G research and testing. Thank you, participants, for participating in today's virtual event. On behalf of Keysight Technologies, I would like to thank you all for taking time out and participating in today's virtual event. Like I mentioned earlier, please take time out to enter your requirements on the survey form, which will be shared to you at the end of this virtual event. Dear participants, we hope this session was helpful to you. This session would also be available on demand shortly so that you can go through this virtual event again. On behalf of Keysight Technologies, we would like to thank you for participating in this session. As you may know, Keysight Technologies runs a series of virtual events periodically, and we'll keep you posted on the next set of virtual events over email and other modes. This virtual event will also be available on demand shortly, and you will get an email once it is ready at the address you would have used for registration. You can view this virtual event any number of times on demand. You can also share the on-demand details with your colleagues, team members, friends, etc., enabling them to register and participate. With that, we would like to sign off this virtual event. All of you have a nice day. Thank you and bye.